All right, so today we're continuing our discussion of equilibrium, and we're going to talk about LeChatelier's principle. So let's just jump right in. This should be pretty much all a refresher for you, a reminder of what we've talked about in class and of what you learned in honors chemistry. So LeChatelier's principle, remember we're focusing on equilibrium. So Henri LeChatelier said that when a system at equilibrium is placed under stress, the system will undergo a change in such a way as to relieve that stress and restore a state of equilibrium. So what does that mean for us? It means that if we stress a system, we take something away, we add something, we change the temperature, we change the pressure, that the rates of the forward and reverse reactions are going to change so that we can come back to a state of equilibrium. So when we take something away from a system at equilibrium, our system is going to shift in such a way as to replace some of what you've taken away. Now remember, this doesn't mean that we're going to come back to the exact same quantities that we had before. But what it does mean is that we're going to come back to that same ratio of products to reactants. If we add something to a system at equilibrium, the system is going to shift in a way to use up some of what you've added. So if we take something away, it's going to shift to replace. If we add something, it's going to shift to use it up. And understanding what's happening at the molecular level, we are speeding up or slowing down one of the reactions. If we add more reactant, we're going to speed up the forward reaction. That's going to cause a shift to the right until we reach a point where that forward reaction and reverse reaction are going at the same speed again. If we speed up the reverse reaction, it's going to cause a shift to the left. So let's look at a couple of examples. First one is just a thermal equilibrium example. We have a closed container of ice and water, and it's at equilibrium. Some of our water is freezing, some of our ice is melting, and then we raise the temperature. This one's kind of a common sense example, right? We all know that if we raise the temperature, more ice is going to melt. And so as we increase the energy, the system is going to shift to the right to restore that equilibrium. Whoops, my word's in the wrong spot, sorry. Okay, different example, still talking about temperature. We have our closed container of dinitrogen tetroxide and nitrogen dioxide, and it's at equilibrium. Not talking about temperature. We're going to add some nitrogen dioxide to the container. So here's our balanced chemical equation. Dinitrogen tetroxide plus energy is going to yield 2 nitrogen dioxide. So if I add some product, then this is going to shift to the left to restore equilibrium. It's going to shift to use up some of that nitrogen dioxide that was added. It's going to make more dinitrogen tetroxide until we reach that same ratio of nitrogen dioxide to dinitrogen tetroxide that we had before the disturbance. Okay, we're back to a thermal equilibrium system again, but again, we're not going to be talking about adding or removing heat. We're going to add or remove water vapor. So we have water, and if you add energy, that converts to water vapor. So if I remove some of the vapor, even without changing the temperature, the system is going to shift to the right to replace what was removed. It's going to shift to the right to restore that equilibrium. Okay, last example here is our closed container of dinitrogen tetroxide and nitrogen dioxide. Again, at equilibrium, LeChatelier's principle always starts with a system at equilibrium. And we're going to increase the pressure on that system. Now remember, increasing pressure is going to be achieved by decreasing volume. So that means that we're going to have increased pressure because we're going to have more collisions with the walls of the container. And so when we have those more collisions with the walls of the container, the way to alleviate the number of collisions is to decrease the number of molecules. And so when we have an increase in pressure due to a volume change, it's always going to shift to the side with fewer moles of gas. In this case, it's going to shift to the left to restore equilibrium because there are fewer moles of gas on that side of the equation. Oh, word in the wrong spot again, sorry. So in general, with LeChatelier's principle, if we add or take away any reactant or any product, the value of K is not going to change. The reaction is going to adjust to that new equilibrium position. So the ratio of products to reactants is still going to stay the same. K is not going to change. So the total amounts of reactants and products may change, but the ratio, that K value, law of mass action, is going to stay the same. What are some of the stress factors that we can talk about? Well, we can talk about a change in concentration of reactants or of products. We can talk about a change in the volume or pressure for gases. So when we change pressure, so if we add pressure or decrease pressure, we add pressure, it's going to shift to the side with fewer moles of gas. If we decrease pressure, it's going to shift to the side with more moles of gas. And if we think about that, that's going to keep Kp the same by keeping that ratio the same. It's also going to keep Kc the same, that concentration, because if you think about changing volume, you're also changing the concentration of the gases. If we change pressure by adding an inert gas, that's going to change the total pressure, but it's not going to change the partial pressures. And so it's not going to change the K value, which means it's not actually going to cause a change in our system at equilibrium at all. So again, change in pressure by virtue of change in volume, not by adding an inert gas. And then the other stress factor is a change in temperature. Now with a change in temperature, this one's a little bit different. When we change concentration or pressure, K does not change. When we change temperature, we know that K is temperature dependent. So when we change temperature, K is going to change. All right, last thing to talk about when it comes to LeChatelier's principle is catalysts. So we know that a catalyst works by decreasing activation energy or by increasing the number of effective collisions, by increasing molecular orientation. But what we also know is that catalysts increase the rate of the forward reaction and the reverse reaction. And so when we add a catalyst, we get to equilibrium faster, but that ratio or that composition is going to be unchanged. So adding a catalyst is not going to cause a shift in either direction. It's just going to make us reach equilibrium faster. So comes more quickly to equilibrium, but K is not changed. As always, if you have any questions, please let me know. I'll see you tomorrow.